In this section, we are going to discuss and look at pointers in Rust. Pointers might be new to you if you don't have a programming background or come from a language like Java or JavaScript. Pointers are extremely powerful and allow us to move and manipulate data. So, in this section, we are going to see what Rust offers us when it comes to pointers. A pointer is a general concept for a variable that contains an address in memory, which that address points to some data. We've already used pointers in Rust, and the most common pointer is a reference. Remember, a reference is with the ampersand sign. These pointers don't have any types of additional capabilities, but a pointer that does give us an additional capability are smart pointers. Smart pointers originated in C++, so it's not unique to Rust. The common smart pointers in Rust are box, which allocates values on the heap, reference counting, RC, which is a reference counting type that allows multiple ownerships, and refmute, which are accessed through refcell, which enforces the borrowing rules at runtime instead of compile time. The first one we will cover is using a box smart pointer. A box is the most straightforward smart pointer Rust offers. This allows us to allocate data on the heap rather than the stack. However, the pointer to the heap data is going to remain on the stack. So let's look at a quick example of using a box. We will create a tuple called t, and we'll give it the values 12 and eggs. And then in here we'll create a box, and we'll call it b, and we'll say box new, and then we'll just have it create a reference, aka a pointer, to t. So now we can print out our new box pointer. And I need to use curly brackets. There we go. So now if we run this, we see that our b variable, which is our box, printed out 12 and eggs. And now, so tuples are created on the stack. And then when we created a new box, it was created on the heap, but b was stored on the stack. And then b just pointed to the address in memory on the heap where this was stored. So pointers also come with a dereference operator. So let's first start out with creating a simple reference. We'll go x here, oh, nope, and x. And x, alright. And now we will make sure that these are equal. And 5 and y. So if we cargo run this, we actually see that we get an error. And it's saying we cannot compare an integer with a reference to an integer. So what we need to do here is actually deallocate our reference by using the asterisk, and that deallocates it for us. And now when we run it, we see that we don't get that error anymore. So deallocation is going to give us the value at that memory address. And then likewise, we can do this with a box. So we will say let x equals 5. Let y equals box new of x, and then we'll do the same exact checks again. And if we run this, everything runs successfully. And then just to verify, if we print out our box, we expect 5 to be returned to us. So let's print it out and just verify. And we get 5. And honestly, that is truly all there is to it for boxes. It is a very straightforward concept, and it's just a way for us to allocate data onto the heap. In most cases, ownership is clear. We know exactly which variable owns what value. But sometimes there are cases where a single value might have or need multiple owners. For example, the graph data struct. If we look in here, we see that we have multiple nodes of 0, 1, 2, 3, and 4. And then each of these nodes has an edge pointing to it. Well, node 0 is connected to node 1 and 4. So we can say logically that node 0 had multiple owners of 1 and 4. So for us to allow multiple ownership, we have RC, which stands for reference counted. RC is also allocated on the heap, and RC is going to track the number of references to evaluate whether or not a value is still in use. Naturally, if there are 0 references, then the value is cleaned up. As a side note, there is also ARC, ARC, which stands for Atomic Reference Counting. It is the same thing as RC, but ARC is designed for safe sharing between threads. So only use ARC when sharing the pointer between threads, otherwise stick to RC. Now let's see an example of RC. So the first thing we need to do is actually bring it into scope. Use standard RC, RC. Oh, that's because I left out. There we go. Alright, so now we have RC in scope. So now we'll say let S1 equals RC new, create a new reference counter, and then we'll say string from, and we'll just say pointer. And then to create references to our string, we'll say s1.clone, and then we can also clone s2 because it points to the same value on the heap. And then just to prove that they all point to the same value, we'll print them all out. We have S1, S2, and S3. And now if we run this, we see that we have pointer, 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 pointer printed out 3 times. So in this, we have an RC value pointed to a heap allocated string, which is going to have a reference count associated with it. Cloning an RC does not copy the value. It creates another pointer to it and increments the reference count. So again, in this example, the string pointer has a reference count of 3, and S1, S2, and S3, which are all on the stack, all point to the string that is located on the heap. And with our data being a string, we are still able to use string methods as usual directly. And I'll show this to you by saying S1 dot contains, and then in here we want to make sure it contains point. And then just to show that all the other ones are able to do it as well, we'll say contains in this one, and we'll say ter. So we would expect our output to now be true, pointer, and true. And we have true, pointer, true, which is what we anticipated. And that's really, again, all there is to it, to RC and ARC. So now in the next lecture, we're going to talk about refcell. Refcell allows us to follow the interior mutability pattern. Interior mutability is a design pattern that allows us to mutate data even when there are immutable references to that data. This is typically not allowed, as we learned earlier in the course, so this does use unsafe code to bend Rust's usual rules of mutation and borrowing. RefCell's rules are enforced at runtime, meaning the compiler typically won't catch any errors for us. So if an error is presented at runtime, then our program will panic and terminate. So let's begin to look at an example using RefCell. The first thing we need to do is import it in, and it is in standard cell RefCell. And now we will create a new struct called flagger, and this is just going to be a simple struct in order to demonstrate the idea behind a RefCell. So we're going to have one field called isTrue that's going to be of type RefCell, which is looking for a Boolean. So now we will say let flag equals flagger is true RefCell new, and then we want our Boolean to be true in this case. So when we use RefCell, we gain access to two methods, borrow and borrow mute. Borrow returns the smart pointer as a ref to t, so borrow returns ref t, and then borrow mute returns ref mute to type t. And both of these implement dereferencing, so we can treat them like regular references. So we'll say let reference equals flag.isTrue .borrow, and now we will print this out to make sure that the value of true is what was borrowed. And we have true. So now we can comment this out, and let's do a mutable borrow. So we'll say let mute ref equals flag.isTrue.borrow mute, and then we will dereference it. That way we can access the value inside of here, which in this case is currently true, so we want to dereference it to have direct access to it, and now we want to change it to false. Dereference first to access inside. And now when we print this out, we expect it to print out false, which is what we got. So we were able to mutably change an immutable value. And now what happens if we comment them both in and then rerun it? So when we comment it in and rerun it, we see that it ran fine, and then it panicked. So when we have them both commented in, we get an error stating that it was already borrowed. And this is because it wasn't checked at the compile time, but it was checked at runtime. So we cannot have multiple borrows out unless we pair it with an RC. So let's see what that looks like. So we will change here to be RC, and then reference, have a ref cell inside of it. And now we will say RC new, and now we can say our new reference here, we'll just delete all of this, is RC new flag.isTrue.clone. And now when we run this, we will need to make that in debug mode. And now when we run it, we see that we printed out a ref cell which points to the value of true. So now we have created another owner pointing to our ref cell which is holding the value of true. And if we wanted to change the value through our shared owner, we can do it this way. So we can say let mute ref equals reference.borrowMute, and now we can change it to false, and now we can print it out again, and it will print out and run just fine, and we have the same results as we did earlier. So let's summarize really quickly on when to choose box, RC, or ref cell. So RC enables multiple owners of the same data, whereas box and ref cell only have single owners. Box allows immutable or mutable borrows checked at compile time. RC allows only immutable borrows checked at compile time, and ref cell allows immutable or mutable borrows checked at runtime. And then because ref cells allows mutable borrows checked at runtime, you can mutate the value inside the ref cell even when the ref cell is immutable. So again, smart pointers are very powerful in allowing us to manipulate data and store it on the heap and allow us to do a lot of very unique things with the values inside. And so we will be able to take these concepts and apply them in the next section when we start to talk about concurrency. I hope you enjoyed this section on smart pointers in Rust. We are now going to take some time to go over to the solution to the assignment, starting with question 1. Which is create a variable on the stack and also create a variable on the heap. Multiply their values and print out the result. So we'll start out with creating a variable on the stack. So we'll assign 5. And now we need to create a variable on the heap. So we'll call it val2. And to create a variable on the heap, we can simply just use a box smart pointer. So we will create a new box which establishes it on the heap, and we will assign it the value of 2. So now our 2 integer is going to be created on the heap. And now we want to multiply their values and print out the result. So we can use the print line macro, and we can say val times val2. So this in its current state will not execute correctly because we need to dereference value 2, and now if we run it we see that we have the value 10. So remember, creating a value on the heap, we can simply use a box smart pointer, and then to get that value off the heap in a format that we can utilize it, we need to dereference the value. So now moving on to question 2, we want to create a variable that holds a string. So we will say let RC value equals string from RC value. Now we want to create a reference counting smart pointer that points to the string above. So the first thing we need to do is actually bring in reference counting smart pointer into our scope. So we can use the standard RC and then RC to bring it into scope for us. And now we can say let RC equals of RC type string equals RC new RC value. So what we're doing here is creating a reference counting smart pointer to our string variable RC value above. And now we want to print out how many references the smart pointer has. So we can use our print line macro, and we can very easily get this value by using RC strong count, and then pass in a reference to our smart pointer. So let's run that to make sure. And we see that we have outputted the value of 1, which is currently correct because the only reference we have right now to RC value is our RC smart pointer. Okay, so now we're going to go down into this code block and we're going to create another reference counting smart pointer. So let's just go ahead and we will copy and paste this. We'll call this RC2, and we want it to point to our first smart pointer, so our RC. So we will call this RC here. And now we want to print out how many references each smart pointer has. So again, we will take this, and we're good there, and now we put 2 there. So now if we run this, what is it? What do we have? We expected a string and found RC, and that's because I did new right here. We want to clone it. So now if we run it, we have the correct results. That's what copying and pasting will get you. So now we see that we have 2 and 2 here, and that is also correct. So now what we have is we have both of these smart pointers pointing to the exact same value on the heap. Therefore, the reference count to that value on the heap is 2. But now we exit out of this code block, so what value is going to be dropped here? Well, RC2 is going to be dropped when we leave this scope because it was created in this scope. So now if we print out how many references our first smart pointer has, we would expect the answer, the value to be outputted to be 1. So if we run this again, we now see that we have 1 being printed out because we no longer have RC2 pointing to that value on the heap. Therefore, our reference count is decremented by 1. So again, we exit out of this scope of code. So what value is going to be dropped here? Well, in this code block is where we created our first smart pointer, RC. So RC is going to be what is dropped here. So now that RC is dropped, what happens if we try to run this code where we try to reference RC value? And remember, RC value is what we used here to create our first reference counted smart pointer. So what do you think will happen when we try to run the program now? Well, I expect we're going to get an error because we moved RC value into our RC pointer. So let's run this and see what we get. So we see a move occurs from RC value, and it's because the move occurred here when we assigned our RC value string to our actual smart pointer, and then we try to use that value after it had already been moved. So basically what happened is once our first smart pointer, RC, was dropped, RC value is also dropped. So hopefully that makes sense. If you have any questions about this assignment, please feel free to ask them in the Q&A section.